So welcome to our seminar series on 3D geometry and computer vision. So today we have invited Xiaowei Zhou from Zhejiang University. He will give us a wonderful talk about the 3D digitalization, about humans and the things. So we also invite two panelists, and Yebing Liu from Tsinghua University and Lan Xu from Shanghai Tech University. So later after the talk, we will have a panel discussion. We will share some our thoughts on some interesting topics. So let's welcome Professor Xiaowei Zhou to give his talk.
Okay, can you see my screen?
Yes, yes.
All right, so thank you, Yang, for hosting this talk and for the introduction. And also thank Qixin for inviting me and organizing such an amazing 3D GV seminars. And also thank Yebing and Lan for joining the panel and waiting until the end of this talk. So today I would like to talk about 3D digitalization of humans and things. So I would like to introduce some of our recent work that aims to make this technology more accessible to everybody. So 3D digitalization means reconstructing 3D geometry, appearance, and motion of humans and things. Once we are able to do this, we can do a lot of cool stuffs. For example, our meeting today can be more immersive. We can jump out of the 2D screen and see each other closely in 3D, as if we are in the same space. Also, we will be able to record the exciting moments and watch them in any viewpoints we like. As you may already know, in GTC this year, Jason Huang, the CEO of NVIDIA, gave a keynote speech with a digital copy of himself, as shown here. And also the background keychain was synthetic. So let's first use Jason's example to see today how we do the 3D digitalization. So for 3D reconstruction, they use a dense array of cameras taking pictures from different viewpoints and reconstruct the 3D model with multi-view stereo algorithms. And there is some manual post-processing. And to capture the motion of Jason, they use an optical mocap system like this. And as this is very time-consuming, they hire an actor wearing a mocap suit and mimicking Jason's movements while watching his speech videos. So from this example, we can see that the whole procedure needs very specially designed hardware and often very expensive. And the procedure is also very complicated and time-consuming and needs to be done in well-constrained environments. And all this is just for making a 14 seconds video. Forgot to mention, only 14 seconds of the GTC speech was synthetic. So we can see that right now this technology is actually not accessible to everybody, and only the professional users can afford. So this is what we want to solve. So let's start from 3D human reconstruction. The question is, can we reconstruct a detailed 3D surface of human body from such a RGB video? If we can do this, everyone can digitalize himself with just a mobile phone. So first, let's look at the traditional pipeline for image-based 3D modeling. So this figure is borrowed from a coalesced SIGGRAPH paper. And there are many steps. So basically from the multi-view images to point clouds, and from point clouds to mesh, and from the mesh to texture mesh. And actually for each step, there are a lot of sub-steps or operations to handle the noises or occlusions. So we can say this is a long pipeline with lots of independent and handcrafted steps. Any mistake in any step may produce artifacts in the end. Also, there is no prior knowledge about human was used. That's why we need specially designed data capture hardware and constrain the environment to make sure everything works fine. So to reduce the requirements on the input, many recent works try to make use of human body prior in reconstruction. For example, building the deformable models of human bodies. So the most famous one is SMPL model, which is a deformable mesh controlled by a set of pose parameters and shape parameters. With this model, we can even do reconstruction from a single image by fitting this model to the image features, for example, the 2D key points or silhouettes. However, this model cannot represent the rich details on the human surfaces, for example, the clothes or hair. And to obtain more detailed reconstruction, many recent work try to use neural networks to directly predict the dense geometry of human body, represented by 3D voxels, or more recently, the implicit functions, so that we can recover more details than the SMPL model, as we can see here in these examples. But it is still very hard to guarantee the reconstruction quality if we just pass a single image into a network without any feedback or optimization, especially for the images very different from the training data. So the most recent trend for solving the multi-view 3D reconstruction problem is so-called inverse rendering with implicit neural representations. For example, NeRF. So unlike previous methods that represent 3D objects as point clouds or meshes, NeRF represents the 3D object as a network. So the input to the network are 3D coordinates and view direction of a point, and the output are the color and the density of that point. The colors and densities of all sampled points in the space form the radiance field, from which we can render 2D images of any viewpoints by volume rendering. So the most important thing here is that both the 3D representation, that is the network, and the rendering process, the volume rendering, are differentiable, so that we can reconstruct the 3D representation by minimizing the difference between the rendered images and the input images. This is important because in this way, we can solve the multi-view reconstruction problem in a unified optimization framework instead of lots of separate steps as we see in the traditional pipeline. So the results are actually very impressive, even for the very complex things or even the transparent objects. Also, we can see that the rendered images are very realistic because in the training, we are directly optimizing the differences to the real images. We are optimizing the photorealism of the rendered images. So can we just apply this kind of approach to reconstructing human bodies? Yes, it definitely works if we have abundant number of input views. For example, like 100 views. But here our goal is to get rid of the dense camera arrays. So we can see here if the input views are very sparse, for example, only 4 input views, it is very difficult to reconstruct a meaningful representation, as the optimization problem is ill-posed. There are too many variables, but too few observations. So how can we solve the 3D reconstruction from very sparse input views? Actually, the key idea here is that we need to make use of all observations from different frames across the video. As the person is moving, so we can have different observations about the person from different frames. So to this end, we propose a method called neural body in CVPR this year. So basically, we assume that the radiance fields of the person in different frames are decoded from the same set of latent codes with a shared decoder. So in this way, we are able to use all the frames in the video to learn the same set of latent codes and the decoder. So to account for the pose change in different frames, actually we assume that the latent codes are anchored on the vertices of an SMPR model, and their spatial locations change with the human pose. So we call these latent codes as structured latent codes. So different poses give different spatial arrangements of the latent codes, which are finally decoded into different radiance fields. And during the training, the human pose can be estimated from the input multi-view images, which I will introduce in the second part of this talk. And from the structured latent codes, we use a sparse convnets to convert the post latent codes into a regular grid of codes. And for any 3D points, we can get its code by interpolation and decode it into the corresponding color and density with a network. So here is a qualitative comparison to neural volumes and the NeRF. And we can see our results are much better. And this definitely because we are using more observations, we're using the multiple frames, the whole sequence to train the representation. While, for example, NeRF actually it cannot represent dynamic scene, so it cannot be trained on the whole video. And the direct application of our approach is that we can produce free viewpoint video using very few cameras, as we can see in this example. So basically, this effect is called bullet time effect in movies, first used in the film The Matrix. And at that time, the bullet time video was captured by a system that requires dozens of cameras, as shown here. In fact, neural body is also able to reconstruct moving humans from molecular videos. For example, these videos are from the people snapshot dataset. The subjects are self-rotating while holding an A pose. So the second and fourth column are the results from the original paper. Basically, they use SMPI model. They deformed the SMPI model to fit the 2D silhouettes in the image. So compared with it, neural body can produce more detailed geometry. Of course, the surface is not that smooth because we extract the surface from the density volume. But there are more details. And a limitation of neural body is that it cannot synthesize images of novel human poses. That is, the model is not animatable. As we can see here, if we repose the latent codes with a novel pose that is unthin in the input videos, there will be unpredictable artifacts in the rendered images. The reason is that in neural body, we use 3D convolution to convert the structured latent codes into radiance fields. And we know that 3D convolution is not equivariant to spatial transformation of the latent codes. So the resulted radiance fields will be unpredictable. There will be a lot of artifacts. So to solve this problem, in ICCV this year, we propose another model called animatable NeRF. So the key idea is that we can construct a NeRF in the canonic space and deform it into other poses. The deformation field can be represented by the linear blending scheme. That is, the transformation of any point in the space is a linear combination of the key points on the skeleton, on the human skeleton. And the blend weights of any point is also represented by a network and learned together with the canonic NeRF. So once we can learn canonic NeRF and the blending weights from the input videos, we can deform the canonic NeRF into novel poses and render the images in any viewpoints. And here is a qualitative comparison with previous methods. Basically, neural textures and NHR, they have 3D features and project the features into 2D and render the image with 2D convolutions. And we can see the results are not very consistent. And we can get much better results by animatable NeRF. So actually, as we have seen in previous example, another limitation of neural body or animatable NeRF is that actually NeRF is not designed for surface reconstruction. So because it represents geometry by densities. If we convert the density volume into a mesh by, for example, marching cubes, the surface will be very noisy and there might be holes, even as we can see in this example. So to solve this issue, actually we can make use of the most recent results in some recent works that replace NeRF with, for example, SDF functions, SDF, for example, news. So the basic idea in these works is that we can represent the geometry by SDF, by neural SDF instead of densities. But during reconstruction, we convert SDF values, for example, the blue line here, into the densities, the red line here, by a sigmoid function, so that we can still render images with volume rendering and optimize SDF. So in this way, we can reconstruct much better surfaces. So this is the results by replacing the NeRF in animatable NeRF by neural SDF. And here are more results from the self-rotating videos. So actually, this video is from People Snapshot. And this guy is Sida Peng, who is the first author of neural body and animatable NeRF. And here shows an application of our method. So basically, we can reconstruct our body models from self-rotating videos using mobile phones, just the videos from mobile phones, and generate all kinds of animations of ourselves, as shown at these 3 videos. So actually, here we use the motion data from Adobe to do the animation. So here we can say another important question is, how can we capture the motion of ourselves? So this problem is human motion capture, which is the second part of my talk today. So the most widely used mocap systems are optical mocap systems like OptiTrack. So these systems can be very accurate and high frame rate, but they need body markers and need to be deployed in very constrained environments. And another solution is the inertial mocap on the right. So the inertial mocap systems basically use IMUs attached to human body to track the body motion. So it can be used in unconstrained environments, but they still need on-body IMU sensors. And because IMUs are tracking the relative motion between time, so there is no global positioning, and there is drifting issue. So in a word, these commercial systems all need special hardware and not easy to use because they need either the body markers or on-body sensors. So the first question is, if we want to make mocap more convenient, the first question is, can we get rid of on-body markers or sensors? Can we recover motion from multi-view videos? So actually in these days, this is not hard because we can easily detect body joints in multi-view images and reconstruct the 3D locations of body joints by triangulation if the videos are synchronized. Of course, to reconstruct the skeleton more robustly, we need to consider more constraints like ball length during the triangulation. And here's a real-time demo in our lab where we are able to capture the motion of human body, face, and hands very accurately in real time, using only 2 web cameras as shown here. But if there are more than one person in the scene, the problem is much more challenging because we need to find the correspondences between detected people across views. So this is not an easy task. We cannot just apply the ReID because there is a large viewpoint change between views, and the 2 people may look very similar to each other. So to solve this problem, our idea is we need to combine the appearance and the geometry. So basically, for appearance, we use a ReID network to measure the similarity, the appearance similarity between detected persons. And we use the epipolar geometry to measure the geometric consistency. That is a point and its match in 2 images. They should satisfy the epipolar constraint. That is, the matched point should lie on this line. And another idea we can use is that the cycle consistency, because we have multiple views. So the correct matches in multiple views, they should form a closed cycle across images. And this cycle consistency constraint can be imposed by a low rank constraint in the optimization. And with this algorithm, we have built real-time markedly small cap systems as shown here, which can capture 3D motion of multiple people with few RGB cameras. And the system can be deployed in both indoor and outdoor scenes, even for very crowded indoor scenario, as shown on the left, and the sports game with very fast motion as shown on the right. And actually, combined with our human body reconstruction methods, we can implement a very low-cost VR sports broadcasting system or holoprotection system. For example, here, for the players, we can do the offline reconstruction. Basically, we reconstruct the animatable 3D models of players with mobile phones before the game using animatable NeRF, for example. Then we can, during the game, we can capture the motion of players using several cameras and use the motion data to animate the 3D models we reconstructed and render them in the VR glasses, so that we can have a volumetric video. We can watch the game immersively with 3 viewpoints in VR glasses. And the whole system is very low cost, just several mobile phones and several RGB cameras. But this kind of system still needs multiple synchronized videos, which is not always available. So the next question is, can we recover motion from unsynchronized and uncalibrated videos? For example, can we recover the tennis serving motion of Roger Federer from those internet videos? This is really hard as the videos are unsynchronized, the camera poses are unknown, and we cannot solve the poses by strike from motion because the background in these videos are different. And even for motions, even the motions in these videos are not exactly the same because these videos are recorded from different games, although they are very similar. So to solve this problem, the key idea is we can use the human body as the calibration target and jointly optimize everything, the video synchronization, the camera parameters, and the human motion. As the motions are not exactly the same among different videos, so here we also model the motion variation, the motions in different sequences by a low-rank approximation. here are some results recovered from the internet videos. So we can see the recovered motion are basically very accurate and very detailed. And another challenge is, can we get rid of multiple views and recover high quality motion from just a single video? So this problem is often called 3D human pose estimation. And when I was a postdoc at Penn, working with Kostas Danielidis, actually I had made many efforts to solve this problem with George Pavlakos. So the basic approach is to use neural networks to regress key points or pose parameters. And actually, we have proposed many different 3D pose representations and the supervision methods for learning. And of course, there are also a lot of fantastic works from other groups that show very promising results. For example, VNect, HMR, Spin, Mono Total Capture, and Vibe. But even until today, I think the problem is still not solved. Here is an example. So although the results, the reconstructed pose seems very reasonable in the original view, if we render it in other views, we can see it is not accurate. The reason is that for single view 3D reconstruction, there is ambiguity, right? There is depth ambiguity and there is self-occlusion. To resolve these ambiguities, we need more constraints. So, for example, in our paper in CVPR this year, we found that in many scenes there are mirrors, for example, in gyms or dancing rooms. And if we can see both the person and his or her image in the mirror, then we will have an additional view to solve the depth ambiguity and observe unseen part of the person. As a result, we can recover the pose more accurately. And here shows how we solve the problem. So basically, we estimate the 3D poses of the persons and their mirrored images separately, with the constraint that the recovered poses should be symmetric with respect to the mirror. But to do this, we need to know the mirror geometry, the normal of the mirror relative to the camera. So to solve the mirror geometry, basically we use the validation points in the single image that correspond to the two sets of parallel boundaries of the mirror. And here are some results. So on the left is the result of Vibe without mirror constraint. And we can see there is jittering and it's not very accurate. And actually the recovered poses are not symmetric, right? And they are not symmetric to each other. And on the right is our result. And we can see that the recovered motion is more accurate and stable. And there are more results on videos we collect from the internet. So what's interesting here is that we found that there are lots of such kind of videos on the internet. It seems people like mirrors very much. For example, this guy, he has a mirror on the facade of his house just to practice golf. So we collect hundreds of such videos from YouTube and build a dataset called Mirrored Human. And here's the link to our dataset. Basically, we only provided the links to these YouTube videos, as well as the recovered motion by our method. As we can see, the collected videos have a huge diversity of subjects, humans, and background. So an important application of our dataset is to train single view method on our dataset, because our dataset provide millions of images with a large diversity and also the pretty accurate 3D poses recovered with the mirror constraint. So we can use these images and the recovered poses as training data to train the single view methods. And here shows the results of MeshNet trained with our dataset. So compared with the pre-trained model, the performance is consistently improved on 3D PW and the human 3.6 minute. Especially on 3D PW, the improvement is very obvious. And this dataset is an in the wild dataset, so which shows that training on our dataset on more diverse data can improve the generalization of the model. So these are our works on human motion capture, and the different settings include mocap from multiple views, from unsynchronized videos and monocular videos. So based on the code of these works, we built a library called Easy Mocap. Basically, the name means to make human motion capture easier. And this data set also includes, this library also includes data sets of multi-view videos and mirrored human. We also provide different, many useful code for example, camera calibration, human pose annotation, and the visualization of 3D motion, 3D skeletons. So welcome to check it out. All right, so we have discussed how to digitize humans and their motions with low cost. Next, I would like to talk about 3D scene reconstruction, which is also very important in many applications. For example, 3D reconstruction actually can give us a full 3D perception of the surrounding environment. This is very important for making realistic AR effects, such as to handling the occlusion and the collision effects. Like this dancing video in the middle is made by the 3D reconstruction with LiDAR on the iPad Pro. Although depth sensors like the LiDAR can provide very accurate depth measurements, they usually use a lot of power. They are power consuming and only available to very few high-end products like the iPad Pro. So a more accessible solution is reconstruction using only a molecular camera, which is immediately available on many phones. However, depth estimation with a molecular camera is not as accurate as depth sensors, and the computation is usually very expensive. We need to compute the depth maps online. So let's first have a look at the traditional pipeline for 3D reconstruction with molecular camera. So basically, keyframes are first selected from the input videos and sent through the multi-view depth estimation algorithm or MVS network to estimate the depth maps for keyframes. And then these depth maps are converted to 3D point clouds and fused into a TSDF volume, which represents the reconstructed surface. And we scan the scene fragment by fragment by fusing, by TSDF fusion. Since we can see the depth maps in the traditional pipeline are estimated individually for each fragment. So they are usually not very consistent in scale and also containing a lot of noises. So if we fuse these inconsistent depth maps, the reconstruction result is often layered or even scattered, as we can see here. Also, there are a lot of redundant computation between the fragments. So these facts are the reasons for the limited reconstruction quality and efficiency of the traditional pipeline. To address these limitations, we propose a new system called NeuroRecon. So the basic idea is instead of first computing depth maps as intermediate representations, we try to directly reconstruct TSDF volumes for each fragment and fuse them in the world frame, in the world coordinates. And this is the pipeline for reconstruction of each fragment. So So we first construct the 3D feature volume from the post images. To do this, we pass the post multi-view images through a 2D ConfNets and unproject the 2D features into 3D space and pulling them to form a 3D feature volume. Then we use a sparse convolution to predict the fragment geometry represented in sparse TSDF volume. A nice thing of using 3D feature volume as intermediate representation instead of depth maps is that when we try to fuse the geometry of different fragments, we don't need to do the fusion in the final TSDF volume. We can do it in the feature space, in the feature volume here. So basically, we can replace the sparse convolution by a gated recurrent unit to fuse the features on the fly for each voxel and use a MLP to predict the TSDF values from the features. So this results in a joint reconstruction and the fusion system, where the reconstruction and the fusion modules can be jointly learned. And here is a comparison to the traditional TSDF fusion. This is the result if we first predict the geometry for each fragment and then fuse them by standard TSDF fusion. We can see that the jointly learned reconstruction and fusion can produce more globally coherent geometry compared to the standard TSDF fusion. And here is the qualitative comparison to previous methods. So basically, we can see NeuroRecon can reconstruct geometry with better quality compared to depth-based methods like CoMap, like DeepV2D, and CNMNet. And Atlas is the state of art for the volume-based 3D reconstruction method. And NeuroRecon runs 10 times faster than Atlas. Also, Atlas cannot be used to reconstruct larger scale scenes, as it tries to reconstruct the whole scene in a batch mode with a large memory cost. While NeuroRecon do the reconstruction incrementally, actually fragment by fragment, so it's much more efficient and can handle a large scale thing. So here are the quantitative results, also showing that NeuroRecon can be more accurate and efficient, and the improvements are large. And the left, here are some demos of NeuroRecon. The left video is using NeuroRecon to incrementally reconstruct our office using the pre-trained model on ScanNet. And we can see that it is able to reconstruct the white walls with no texture. And the pre-trained model also works for outdoor scenes without training on outdoor data, as shown on the right. And there are some AR effects simulated based on the mesh generated by NeuroRecon. So we can see here the falling blocks and the clothes are simulated. Actually, we imported the mesh reconstructed by NeuroRecon into a physics engine to simulate these effects. All right, so this is pretty much I would like to share today. So in summary, I have introduced some of our work to make 3D modeling of humans and scenes more low cost and convenient. And for these works, I think there are several key factors that make this possible. First, we have more powerful tools like deep learning and more 3D data to learn the prior knowledge about humans and scene structures, so that we can reconstruct from very weak input, for example, a video or even a single image. And also we have better 3D representations, for example, neural implicit functions and differentiable rendering that can make the reconstruction problem to be a unified optimization problem in which we can optimize everything jointly based on input images. And we can add all kinds of constraints like the smoothness constraint or planar constraint easily. More importantly, because we are minimizing the rendering loss, actually we are optimizing the photorealism of the reconstruction. So the reconstructed results can be, especially the rendered images can be very realistic. And of course, there are more challenges to be solved. For example, can we reconstruct from internet data or historic data? For example, can we make Einstein alive again? Can we build a digital human of him? And another direction is, can we recover more properties of the scene? For example, the lighting, the material, and the physical properties like dynamics. And also, I think it is still an open problem to represent general dynamic scenes. Although there are many very good works like NeRF, like deformable NeRF, they have proposed some ways to model the dynamic scenes, but I think there are still more to investigate. And also, I think it is very interesting to do 4D synthesis. That is, can we generate the volumetric video? So at the end, I would like to thank the students in my group who contribute to these works. And all the code of the works in this talk is available on the GitHub page of our group. And actually, there are some other interesting works like DeepSlate for real-time instance segmentation, like Laughter for the feature matching, the image feature matching, and the PVNet for 6D object pose estimation. So welcome to play with them. So this is the end of my talk. Thank you.
Okay, thanks, Xiaowei, sharing this nice work. So let's see whether we have a question from our audience. Yeah, and I can see on the YouTube, I think we have got one question. So the question is related about the hand joint estimation. So, okay, the question basically says the hand joint estimation is quite hard. So how can we improve hand joint estimation in the wide? So shall we? Yeah, do you have any idea?
Yeah. I think this is a very challenging problem. I think the main issue is the the resolution of the image, I think. So basically, if we can have high resolution images like this, if we can see, for example, if we can see the joints very clearly, right, of the hand, basically we can recover them. We can recover the 3D structure and motion very accurately. But in the wild, usually we cannot see the joints very clearly. So in this case, I think a more reasonable way is to one way is to just estimate the whole pose, like for example, the mono. We can use the parametric model, right? We just predict the pose parameters instead of the separate joints. And another thing is that we need to actually, in some applications, we don't need to recover the accurate motion. We just need to recover some gestures, right? For example, in conferencing, we just need to know, oh, this guy is waving his hand or do some gestures. We don't need the precise motion. So in this case, we can combine the image-based estimation with, for example, the semantics or physics-based simulation to solve the problem. Yeah, this is my thought.
Oh, thanks, Xiaowei. So I have got some questions. So maybe I can start. So later, Yebing and Lan can ask other questions. So the first question is about the neural SDF. So So we know the neural STF can help to improve the surface quality. So,
Yeah.
but in the other side, so we lost some color information or texture information. So because for the neural NeRF, so we can recover this nice color information. So do you think how to combine the neural STF and also to preserve the color information for the human reconstruction?
I see. Actually, here we have color, but we just show the surface, the geometry. So basically, in news in this paper, there is also a color network, right? So basically, they just convert SDF to densities, and they have a separate color network. So they still have densities and colors. They render it
Okay.
using volume rendering, similar to NeRF. This is what we do here.
Okay, I can see. So we're still using some neural rendering. Okay, gets the
Yes.
result. Okay. Another question related to you have using some mirror image you did so to recover the pose to estimate the human pose. So do you need some special network to detect the mirror, or you just have an annotation for this mirror? Yeah.
Yeah, actually, in our paper we just annotate that because in this actually in these videos the mirrors, actually the camera is fixed, so we only the position of mirror is not changed across the video. We only annotate the first frame, so
Okay.
it's not hard. But yeah, I think there are also I think there are some automatic methods for mirror detection out there, and definitely we should try them.
Yeah, because you also have two human inside of your video, so maybe you can get two skeleton, so you can get some rough estimation about where the mirror is. Yeah.
Yeah.
Okay, thank you. And so Yibing and Lan, do you have any question related to Xiaowei's work? Xiaowei's work presented today?
Yeah. Hey, Xiaowei. Yeah, thanks for the great talk. Actually, for the neural reconstruction task, I have a question. Yeah, like, could we handle topologic changes like moving the clothes or during the during the neural body reconstruction? Yeah.
Yeah, this is a good question. Actually, in neural body, we didn't explicitly model. We didn't explicitly model the clothes. So basically, it's a part of the radiance field, right? And actually here, let me go back to the. Yeah, so basically here, we use a proxy geometry, the SMPM model. It doesn't include the clothes, but our hope is that the features anchored on SMPM, they can encode some local geometry and appearance of the body, for example, clothes. So so basically in neural body, we didn't explicitly handle the clothes, but I think yes. This is a limitation of neural body. It can handle some tight clothes, for example, this example, but for more loose clothes, like I think we didn't try, and I don't think it can handle very well. But I think a solution is we can use some parametric models that can model the clothes as the proxy geometry, and probably we can solve this problem. And I think another solution is if we want to do the performance capture, actually we can do some offline reconstruction. For example, using the animatable NeRF from the self-rotating video, and we can get better geometry of the person, and using that as the proxy geometry in neural body to do the performance capture. This yeah, these are just some possible solutions. And for the topological change, I think it is not an issue for the implicit functions. Yeah, this is my opinion.
Yeah. And yeah, actually, I have a huge interest like extend the human lightweight human modeling capture neural reconstructions to a more compressed scenarios like human object interaction scenes. Yeah, so I think would it be possible to combine the, for example, like combine the neural body and the neural recon so that we could reconstruct not only the humans but the human interact with some objects like sofas or some dolls or some tools in our hands, so that we could just put them into a VR or AR games, for example. Yeah, it would
Yes,
be
yes.
interesting. Yeah.
Yeah, this is interesting. Yeah, and actually, I think actually I think the neural recon, the neural body and the neural recon, they are very similar to each other, because we in both works we use the 3D features, the 3D latent codes to represent as the latent representation, and decode the geometry or appearance from the latent codes. But the difference between neural recon and the neural body is that in neural body we need to make use of the deformable model, the SMPL, to establish the correspondence between different frames, because the human motion is non-rigid. And we need better constraints, we need better priors to establish the correspondences. But in neural recon, for the rigid scene, the correspondence can be found easily by the camera pose. If we can track the camera pose, we have the correspondence. So this is the main difference. And in future, definitely I think we can combine them, because the underlying representation and the whole pipeline actually is very similar. Yeah.
Yeah, great. Thanks again for the fantastic talk. Yeah.
Thank you.
Hi, Xiaowei.
Hi, Yabi.
Hi, very nice and impressive work. Thanks. And I have only a question about you showed using a monocular camera to capture the static human avatar. I think the quality is very good and very impressive. And you mentioned that you use NeRF to replace the nerve, right? And then refine the geometry. And
Yeah.
I'm wondering, is this your work published or just to modify?
It's ongoing. It's ongoing.
Okay.
Yeah, but we
Mm.
cannot say too much because of the CVPR new regulation.
Okay. Okay, I see. Thank you. Thank you. Mm.
Okay, thank you for sharing your thoughts. So maybe we can move to our panel discussion. So we have prepared some just general question to initialize our discussion. So my first question is, I want to hear your opinion. So what's a good representation for clothes? Because we have seen for the human body, we have a lot of approach to handle the clothes. So in your opinion, what a good representation for clothes should be? Yeah. So what kind of criterion for this good representation? Shall we? I think you have some the work using some NeRF also it's kind of SDF. Yeah.
So actually, I have to say I don't have a very confident answer for this, because actually I didn't have too much work on clothes modeling, but personally I feel that if we just want to do the 3D reconstruction or performance capture, clothes is not an issue for example the implicit functions, because they can handle the topological change very well, right? If we just want to capture the appearance or geometry of clothes from the video. And I think here the real challenge is how to capture, how to model the deformation field from the observation from the video if we use the implicit function as a representation. So, I think also in many applications, the focus is animation, right? We want to simulate the video for new poses, for new motions, and we want to see the realistic motion of the clothes moving with the body. So in this case, I think right now for the time being, the good solution is still mesh, right? Because we can use the existing physically based simulation engines. But in future, I think there are also more and more work to learn and to predict the dynamics using learning, using neural networks. So if we can learn and predict the motion using, for example, also using neural representation, I think this is a very promising and a good way to explore. Yeah, these are just some my personal thoughts. Actually, I'm not an expert on this.
Yeah, thank you. So I think you should have a lot of experience during the human capture, yeah, because the clothes may make a lot of occlusion, yeah, for capture.
Yeah, I think clothes. When we mention clothes, I think more of our goal is to do animation, to let the garment do a realist motion, and also like to do virtual try on, and also like to do garment transition or garment style editing, like this task. So I think the current research is still a long way to go for this kind of task. And in computer vision domain, there are some representation like using unsigned distance field and to model the closed on it, and also using UV distance offset parameterized on the simple model. And all of the most of this work is still low quality and depend mostly on the simple model to get the connection implicitly or explicitly, and I think this is far from enough. And in the graphics domain, the quality is quite good, but they specific on a specific garment and do physics simulation. Although some of the neural techniques now can do neural rendering but they are still specific on a specific garment. And I think there's a long way to go. Maybe still need I agree with Xiaowei that the key is the deformation of the motion. I think this is very important. And also in vision domain, I think we can also consider like combining the neural SDF with neural rendering techniques and to improve the quality of the rendering. Although the geometry reconstruction or deformation of the clothes is not enough accurate, but the rendering result will be improved, and this may be the future possible way to consider. I think this is my thought. Yeah.
Thank you.
Yeah, From actually, I totally agree with Yebin and Xiaowei, especially from the side of view from vision and graphics communities. Yeah, and personally speaking, I would like to see if it would be possible to combine like a parametric model of each kind of clothes, like skirt or t-shirt or shirts or pants. Yeah, and then conditioning the motions on top of it to capture some more reliable motions of this kind of clothes, and then maybe combine the new rendering techniques to generate realistic appearance on top of it. Yeah, and I thought it may be maybe one of the possible solutions to build a bridge between the computer vision and the computer graphics communities. And actually, I think maybe the dataset itself would be a key issue to solve or build this kind of bridge. Yeah, and it still need a lot of efforts to build up this kind of dataset. Yeah, and persuade this kind of connections between this kind of two communities. Yeah.
Okay, thank you. Another question is related to the dynamic capture of multi-person. So we can see there's a trend using this neural approach to reconstruct maybe a single person. And do you have some thought about the possibility of using the neural approach for the multi-person capture and or understanding their action or to understand how they interact between each others? Yeah. So basically, it's the possibility about the neural approach for the multi-person capture.
Yeah, maybe let me start. So I think there is a very nice work from Yebin this year for reconstructing multiple persons using several RGB cameras. And actually, maybe Yebin can discuss more later. So actually, for example, the methods like neural body, they can very naturally extend to handle multiple person, because here actually we have a parametric model for each person, right? If there are multiple persons, we can first detect the persons and model the rough motion by different SMPM models and train the multiple neural bodies simultaneously. Yeah, actually, we have some results. Maybe I can show a little bit here. Can you see the video?
Yes.
Yeah. For example, this is the our extension of neural body to multiple persons, and this is the I think there should be six. We use 6 cameras, and there are three people interacting with each other very closely. And the first on the left is the free viewpoints, the novel view synthesis of the original scene, and also we can edit the scene by, for example, removing one person and removing both persons, and get this kind of results. And yeah, and we here is another video. Yeah, we can also synthesize the normal views of the basketball, and we can also remove two players, and there is only the basketball. There is only basketball left. So this is interesting. So basically we can extend the neural body to handle multiple persons, and actually the main challenge here is, if we are building the radiance fields for different persons, how to model the interactions between different neural radiance fields, right? And And we need to know, so which we need to do segmentation or clustering. We need to know in 3D space which point correspond to which person. This is what we solve in this new work. Yeah, and basically here for these videos, we don't use any segmentation networks. We just optimize everything unsupervisedly, including the neural reference fields for different persons and also the segmentation of different persons. Yeah, I think extending to multi-person scenario there is a huge possibility for this kind of neural representation based methods.
Okay, the video is cool. Yeah.
Okay. Yeah, I think multiple person is a very interesting and promising direction for research, and the promising idea for doing research here, I think, is the as mentioned by Liu Yang, how to applying neural approach to this problem. And I think there are in traditional optimization method need many steps, like a 2D feature or heat map or skeleton detection, and then multi-person segmentation, and also 3D skeleton or 3D simple estimation, also the surface geometry reconstruction, and then appearance reconstruction. And there's a long step, many steps to go. But now I think Xiaowei's work also demonstrate that in the future next year, there's many. I think they will appear an end-to-end approach of solving this problem, and including segmentation, including surface geometry or surface reflectance reconstruction. I think all this can be done end to end, and this is very possible. And yeah, and I think also the association problem here is also important. You need to distinguish or disentangle the multiple persons in 3D, and this also can be end to end. Yeah.
It's promising.
Yeah. Yeah, actually, I also agree that the multi-person scenarios will be super promising for future research direction. Actually, it's very similar to human-object interaction scenes, because in such a scenarios, different instances like humans and objects will occur to each other. And yeah, actually, we have a similar work in SIGGRAPH this year, last year, and basically we model different persons in the scenes using the neural reference fields, so that we could do some post-processing for visual effects like enlarging or synchronized in the time domain. Yeah, but I think it's super promising, like do it in an end-to-end manner to optimize the segmentations and also the neural reference field decompositions in an end-to-end manner. And finally, I would in my opinions, maybe the occlusion would be still an key issues in such a scenarios. Like if two people are interacting to each other in a very close scenarios, like they harm each other, it would be super difficult for the neural reference fields to model them separately. Maybe it would be nice to even optimize them together, just like to handle the topological changes in the single person scenarios. Like we could model the two people's motions to model their motions in a topological changes aware manner. Yeah.
Okay, thank you. So any other topics you want to discuss? If you have some some idea? So if not, well, I can continue. Yeah, I still have one question for discussion. So. Okay, maybe I can continue. Yeah, so it's quite general questions. So so we can see in our, especially for research, people are looking for some low cost solution. Yeah, because we want to minimize the computation cost or minimize the use a lot of hardware. So, but on the other hand, for industry like the movie or some field that people want to like have very high quality result. So do you think how to balance this low cost, or how to say, in another way, we want to use the low cost to achieve high quality with low cost. So do you think it's possible to achieve this goal? Yeah. Yeah, because we have seen a lot of research. People have invent many good algorithm, but maybe it's still not good enough for achieve some standard as required by the industry. So we still can see for the mocap. So people in the industry, people still using this mark. So although we have a lot of markless algorithm, so do you think how to say what's the main challenge to push this markless algorithm to the industry? Yeah, well, what kind of challenge we still need to solve? Or we have solved this challenge, that just the people didn't realize to use this. Yeah.
Yeah, I think maybe Yebing can start discussion because I know that he has some commercial systems for the market mocap, and
Okay, I will start. I think Xiaowei has showing some very interesting application in the talk, like the monocular capture of the static avatar, and then doing free view synthesize for multi-person playing basketball, like in VR. And I think this is very interesting and quite promising. But I think the key problem is for this VR application, the realistic and is still an issue maybe. And so talking about realistic, I think Facebook's works building very large system and to do coded avatar of the very high quality realistic human, and I think it's very a good way to do and the right way to do. And but talking about the low cost way, I think we need to integrate many of different research together. Like if you use multiple cameras, sparse cameras, or just a single depth camera like this setup, it is quite convenient and not that expensive. And I think the way to do the reconstruction here or performance capture is need to combine some face research or head modeling, face modeling, and also hand integrated with the human body. Here the problem is the low resolution of the camera we get, and when we capture the whole body. I think maybe in the future some engineering work can be done here for this kind of thing. And I think the more practical way to do commercialization is the motion capture. For digital character or digital human, the motion capture is on a good way to be markless motion capture. I think maybe a good way to do business application, and because it can use in many applications, and I think it is quite practical now, and it do not need a very high accurate geometry or appearance reconstruction, but the motion capture itself is can using multi-camera system. I think maybe this is good enough for some application. Or just a single depth camera, like our work in double fusion. I think it is still the best motion capture for human body using just a single camera. The problem is how to integrate hand motion and face motion together. This is my thought.
Thank you. Okay, any at all?
Yeah, maybe I could continue so that, and then Xiaowei could finally conclude our ideas. Yeah, yeah, and actually, for me, actually, I think both way are right for commercializations. Yeah, like the high-end solutions and the low-cost solutions, and then the future. Actually, I think the future is in the actually is in between, you know, right? Because I think actually the high-end solutions is quite successful in the movie industry already, because we already use this kind of solutions, mocaps, in even volumetric capturings and sculpturings, modelings in movie industry a lot. And actually we already, even I could say, we already recovered the uncanny valley, you know, in the movie industry, even from 90s, right, in those Hollywood movies. And then this year's actually here is another trend, both in the industry and both in the research communities. Like we are covering the uncanny valley again, but with low cost, no human, low manual labors, and even no artists in the loop. And maybe we are still on the way. And basically, personally speaking, I think maybe we already not in the lowest point in the uncanny valleys. We already climbing the another side of uncanny valley again already. So I think it's the right track to continue the research and even commercializations on the low cost side. And then I think the high-end solutions could provide powerful data set collections, and even you could already commercialize a lot using multi-camera systems these days already. Yeah, and then we could already build some business models using the high-end solutions and collect data sets for the low cost size. And then the low cost size, yeah, I totally agree with Yebin. Maybe the market's motion capture would be the most available way for commercializations in a lot of VR AR applications. Yeah, I don't want to say the word, but maybe metaverse is so, you know, popular these days, but it's VR research community, maybe metaverse is too far away from us. Yeah. Yeah, but yeah, maybe the market's motion capture would be super popular in metaverse because everyone could use it to communicate with each other using the virtual avatars controlled by themselves. No icons, no artifacts. Yeah, it would be super cool. Yeah, and then digitalizations would maybe not that easy because we are still on the other side of uncanny valley, and how to persuade more realistic human digitalizations in a low-cost solutions is we are still on the way. But I think it takes time, and we are on the right track already. Yeah, that's good. That's super good.
Thank you.
Yeah. So basically, I totally agree with Yebin and Lan, and I only have two personal opinions to add. The first is I think the using low cost or high end capture systems, this is an issue of input, which means it depends on it depends on the applications. In application, which capture system we can afford. So if we can, for the neural representation based methods, for such kind of algorithms, if we can have very high resolution input, very dense views, we can also get very high quality in reconstruction. So this is not, I think this is not an issue of the algorithm, but the capture, the hardware, the input, what kind of input we can afford in applications. And another thing is that another point is that I still believe in believe that I think in many applications the photorealism is what we need to pursue instead of the precision in geometry or the accuracy of motion. That means I think the precision is not equivalent to photorealism, because, for example, in a lot of virtual humans or virtual avatars, we can produce very high quality, high resolution models, even with hands, right? But if we do the animation, we animate them, we make films, they seem not realistic. We know they are virtual. But in some recent works, for example, using neural rendering to synthesize for example, the talking videos or the something like this, or something like NeRF to do the normal view synthesis, even if the resolution is not as high as the traditional graphics method, the photorealism is very good. We cannot differentiate between the synthesized images and the true images, because for these neural rendering based methods, basically we are during the learning we are optimizing the photorealism. We are just compare the rendered image with the output image. We are optimizing the photorealism. So I think this should be the objective in many applications we should pursue, instead of just the resolution or precision. Yeah, this is my personal feeling.
Okay, thank you. Thank you. So it seems we have spent a good time on this seminar talk. So probably we can conclude our talk right now. So we thank Xiaowei he has shared a wonderful research progress on the human and scene reconstruction and capture. And we also thank Lan and Yebing to share a lot of thoughts about some interesting topics. So that's the end of this talk right now. We'll see you next time.
Thank you.
Thank you.
Yeah, thank you. Bye.
Bye.